Welcome to this video on the topic of trigonometry. In this video, we're going to have a look at how we can use the trigonometric functions to analyze right-angled triangles. Over here we have a right-angled triangle. We know this is a right-angled triangle because there's a right angle on it. The right angle denoted by this box seen over here in the corner, and we know a right angle is always 90 degrees. Now the next feature we turn our attention to is the side that is opposite the right angle itself. This side over here is the biggest side within the triangle because it's opposite the biggest angle within the triangle, and we call it the hypotenuse. You might remember the hypotenuse from your studies with Pythagoras' theorem. Now the next feature we turn our attention to is an angle, the angle of which I like to call the angle of interest. In this case, we call the angle of interest theta. Theta being a letter from the Greek alphabet. Now since we have this angle over here named as theta, or this angle is our angle of interest, we're able to label the final two sides within our triangle. Opposite the angle of interest theta, we name this side the opposite side. Of course, the opposite side is always opposite the angle of interest theta. We can abbreviate the opposite side down to just an O. And finally, the last side that we need to label is called the adjacent side. Adjacent meaning next to. So what we've got over here is a naming convention we can use to talk explicitly about all the features within this right angle triangle. Now this is important because the sides of right angle triangles form predictable ratios, and using the trigonometric functions we can describe the relationship between the side length ratios and the angle of interest theta over here. So what this means is that given a value of theta, we're going to get an expected opposite and adjacent ratio, so opposite divided by adjacent. We're going to get an expected opposite divided by hypotenuse, and adjacent divided by hypotenuse. Now these are described by the trigonometric functions, or as some people like to call them, the ratios. So the ratios being what we see on the right hand side of the equal signs here, 3 of them, and the function itself what we see on the left. So we have sin, cos and tan. Now these are shorthand for sine, cosine and tangent, but you're welcome to just call them sin, cos and tan, it doesn't really matter. Now the way in which we remember these ratios is we have a mnemonic. We say so, ka, toa. And we say it a lot until we remember it. So we go so, ka, toa. So as in S for sine, O for opposite, H for hypotenuse, ka for cos, adjacent, hypotenuse, and then finally toa for tangent, opposite and adjacent. So we just say it lots and lots of times until we remember all of these ratios so we never forget it ever. Now this is great because these ratios or these functions over here describe the dimensions of right angled triangles. If we go down over here, what we have is a right angled triangle. All of the features on this triangle have been given quantities. So all of the side lengths here, all 3 of them, each have a unique quantity, and an angle of interest that we have over here also has a quantity. What we're going to do is we're going to use these trigonometric functions and ratios to verify that the sine, cosine and tangent ratios yield expected results. So what does that mean? Well, we're going to say, let's make sure that this side, and this side is all possible given this angle. Now starting off, we'll start with sine. And what we're going to do is we're going to make sure that this ratio and this function both agree over here given these quantities over here. Now to do this, we first have to label the triangle. Now obviously this is going to be our hypotenuse, then this must be our angle of interest, this has to be our opposite, and this must be our adjacent because it's left over. What we're going to say is that our ratio is so sine theta equals opposite over hypotenuse, and therefore when we plug in the values we're going to expect to see sine of 22.62 is equal to, on the right hand side, we're going to expect to see 5 divided by 13. Now, you might be feeling a bit lost as to why we're bothering to do this, but what we're going to do is we're going to verify that the value that we see on the left hand side here is going to match up with the value we see on the right side here. Now at this point in time in our math journey, we don't know how to compute the left hand side over here in our head. So what we need to do is we need to use a calculator. So what I'm going to say is up we come to the calculator, and what we've got over here is a fancy graphics calculator. To do these problems over here, we have to be in mode 1. So I go 1 like so. Now next step is I'm going to put in sine 22.62. Now I don't have to use the parentheses here, but I always like to use them because it reduces ambiguity and there's less chance of error when I'm putting problems in. So I just put this in like so, and then I'll go execute, and it's going to tell me this decimal over here. So what we can see is that sine 22.62 is equal to 0.38. So we'll go 2 decimal places. Now for this triangle to work, then what that means is that this ratio on the right hand side over here must also be 0.38. So to verify that that's going to work, what I'm going to do is I'm going to put this ratio into this calculator. So 5 divided by 13, it's going to give me a decimal. I want when it gives me a fraction, I want the decimal, so I go standard to this, and it's of course the same value. So what you can see is that the function itself, given values of theta, so angle of interest, they're going to align with the ratios formed by the opposite side with the hypotenuse. Now this is the same for both cosine and tangent. If we go for, say, cosine, then what you indeed see is that the function itself, so the cosine function, is in agreement with the ratio formed by the adjacent and the hypotenuse sides. So what we can see here is that the dimensions given in this triangle work, and we verify that using these, or this ratio and function together. And finally, if we do this with tangent, we're going to expect to see the same result when we go 5 over 12. And lo and behold, they're exactly the same, albeit expressed to different significant figures, so 0.42. So in summary, what we had a look at in this video was firstly, how we label the sides and the angles within a right-angled triangle. Secondly, we had a look at the trigonometric functions and their respective ratios. And then finally, we had a look at how we can apply these functions and ratios to verify that this triangle indeed exists, or conversely, we made sure that these functions actually work given the premise that this triangle is exact.